We will. Yeah, go. Let's go. Okay, so no. Properties of logarithms. Quick. Okay, I want to kind of. Here's how you can understand this. What logarithms do. Logarithms do something useful for us when we're doing algebra. If you think about the order of operation stuff, kind of think about it as a ladder where you're starting with easy and you're getting harder. Start additions if you're going bottom up, right? If you're isolating, for example. Bottom is addition, subtraction. Next layer up is multiplication, division. Next layer up is exponentiation, and then finally you get up to grouping stuff. What logarithms do is there's some properties that allow you to move down that ladder and get one step easier with logarithms. And so, for example, the product property says that if I have a log, and it doesn't matter what base I'm using, we'll typically use a common log, which is base 10, so we don't even write the b. Or we'll use a natural log, a base E log, and we write that as ln, right? I mean, but we could use any one. It doesn't matter. Any base we choose, the log of a product is equal to the sum of the separate logs. So if I have the log of whatever u is and whatever v is, the log of the product of u times v just equals the log of u by itself plus the log of v by itself. Okay, so there's one. And notice what that does. It takes us from the multiplication rung down to the easier addition rung. Quotient. If I have the same kind of deal, doesn't matter what base. If I have the log of u divided by v, so u on the top, v on the bottom, then that becomes the log of u by itself minus the log of v by itself. So whatever's on the top goes first, and you subtract from that whatever's on the bottom. Okay? And then finally, we have the power property that says if I have the log of a power, right? If I have the log of u to the n, this is probably the easiest one in a way. All you do is you just take the exponent and stick it out front. Okay, it becomes a coefficient. So it just becomes n times the log of u by itself instead of the log of u to the n. Okay? So try this. Not hard stuff. What is that going to become? Now let's break this up into steps here. What can I do with this using my properties of logs? Okay, good, because I've got a y on the bottom. I've got the log of, and I really probably want to have parentheses around this because I'm doing the log of the whole thing, right? So I've got the log of a quotient. Whatever's on the top goes first. Whatever's on the bottom, I'm going to subtract from that, right? So wouldn't you agree that just becomes the log of 7x cubed minus the log of y, right? Okay, but what can I do to that first one? There's some other stuff going on. Okay, good. I've got two things being multiplied, right? I've got a log of 7 times x cubed. So I can take this one and break it up into the log of 7 plus the log of x cubed. And there's still one more thing to do. Okay, good. We've got this 3 that can go out front. I'm taking the log of a power, so the exponent I can pull out front. So the very last step would then be to pull that 3 out in front. Okay, so it would just look like this. All right, so there's first step. And then we can take that 3 out front and make it 3 times the log of x. Okay? So so we can expand these logs. They look a lot bigger, but the individual logs are simpler, and that's the important thing. No, just put the 3 in front of the log is fine. That time sign is just optional. I mean, we know it's there. It's implied multiplication if it's next to the log. You know, good question. Okay, so what about this one? What can I do with that? If I have a log of, and I probably should do this. If I have a log of a product of 3 things, what do you suppose I do? Yeah, expand it out into a sum of 3 small logs. Right? The log of the product of 5 times n is just the log of log 5 plus log of m by itself plus log of n by itself. Right? And then that guy right there. Okay. Right, so we could split, we got the log of the 8 times x cubed is going to allow us to split that into 2 separate smaller logs that are added. Correct? Do that. So first step would be probably to split that 8 up. So I get log of 8 plus log of x cubed, but then the log of x cubed, I can still take that 3 out in front because it's an exponent. Okay? So no big deal. That stuff's not hard to do. Now, we can also do the reverse. What could I do to that guy?
Nothing.
No, I could. There's a lot of stuff I could do to that. What could I do? We got to kind of work backwards here. Well, first of all, if I see a number out in front like this, what can I do with that? Okay, that's a power, so I can move that up to an exponent. If I'm doing the opposite, if I'm, instead of expanding it out into a whole bunch of small logs, I'm going to contract it or condense it into one big ugly log. So the 2 goes up there. So this one becomes, this one becomes log of 2 squared. Now what about the plus sign? That's multiply, right? So these two are going to combine into log of 6 times, whoops, not 2, 6 times. 6 times 2 squared. Then what about the minus log 3? Yeah, so it's all going to be divided by 3. That's going to go on the bottom because of the minus sign, right? And then I could take all that stuff and simplify the numbers a little bit too then. Right? But we won't worry about that. I'm going to give you guys, it sounds harder, but it's actually easier. I'm going to give you problems focusing where to use variables instead of numbers more. So you don't have to worry about adding all the numbers together and using, simplifying the fractions and that kind of stuff. I don't want you to focus on that. I want you to focus on just the properties of logs for now. So it's easier to actually to do with variables because the bases are easier to see. Like this one. Okay, what about that one? Where now we get a t in there instead of a number. Okay, so yeah, so the plus sign means I'm going to multiply. What about the 3? So the 3 is going to go up to the power, right? Does that make sense? So we get a product of this times this, and then the 3 becomes the exponent of the t. Okay? No big deal. Okay, what about that one? Last one. Now, what does it mean here if I'm subtracting all that stuff? Where's all that stuff going to end up? On the bottom. Travis, drop your phone. So all that ends up on the bottom, right? So this is on the top. All that's on the bottom. Now, what's the top going to look like then? If I have a 3 out front on the top, I'm going to get my x cubed, right? On the bottom, I'm going to get 4 times y, right? It just looks like that. Okay. All right. Last issue. How do you deal with stuff like what if I have log of 7 base 3? Your calculator doesn't have a button for that. How do you deal with that? Extremely simple. All you do is the log of u, whatever that is, base c, whatever that is always just equal to the quotient of log u divided by log c. In any base you choose, it doesn't matter. So why not choose an easy base? Why not choose one that's on the calculator, like base 10, which is just a common log? That's the log button on your calculator. Or even better, why not choose base e and just use the natural log? Right? So the log of u base c is just natural log u over natural log c. That's how you do it. Okay? Make sense? And that's, I don't think there's, like, if we wanted, I mean, I could do an example, but this is all it would look like. If I did the log of, let's say that we do the log of 7 base 13, I would just in my calculator literally do natural log 7 divided by natural log 13 and hit enter, and that's my answer. Yes, sir.
This is kind of a silly question, but when would you use logs?
Okay, logs are probably the most valuable thing you could ever use in math, logs and exponentials. Almost everything in the world is described by an exponential function or a logarithmic function. If you wanted, I wish we had a little more time to go into those applications and look at the math of this, but if you wanted to look at any kind of, let's say, a money growth in an account, you wanted to look at radioactive decay, you wanted to look at a population growth of bacteria or people or animals in a forest, or it's all this stuff. That's what this does. Any kind of naturally occurring population-based phenomena that, it's interactions of lots of things is described by this. This is what it does. So it's, in a way, it's absolutely the very most interesting and most useful thing you could possibly do, and it's what you kind of get to do next year, but it's sort of where we get to this year. But it's something you'll see a lot of. I mean, if you were going to go into any kind of science or, sort of economic-based, anything like that, or if you're going to study sociology or psychology or any science, I mean, you will do a ton of this stuff.
I don't get how this applies though to that.
Well, because these are the functions that describe it. So if I wanted to look at, like, for example, if I want to look at population growth, and I'll just give you a quick example now, and maybe we can talk more about this later too. If I look at population growth, a population growth curve always looks like that. Always looks like that. That's what we call that's just an exponential function, right? And so populations start off slow, but if there's unlimited, this is interesting. If there's unlimited resources, they just explode, and that can be a problem. So what happens if there are limited resources? Well, if there are limited resources, then it follows a curve more like this. And that's called a logistic function, which is also based on this stuff. So the population gets real big, they use up too many resources, a bunch of them die off, and then they hit a steady state, and that's typically, and then it eventually happens again. But that stuff's all described by the mathematics that we're just getting into now. If you want to look at radioactive decay, here's the amount of plutonium. If you let it go for a long, long, long time, that's the curve it follows. Okay, where this is like the amount of plutonium, and this is time. Okay, so just to make a really short answer, there's just almost unlimited. I mean, this is just about everything in the real world is described by these mathematics. Okay. Whoa, that was a shot. Yeah. Okay. Let's go to